McDonald's has this Monopoly game where they advertise that 1 in 4 wins, which is 25%. So they're claiming that you have a 25% chance of winning. Say you actually play this game 530 times and you won 108 times. What is your win rate? 108 out of 530, that's about 20%. Is something wrong here? Is that too low? McDonald's claims that you have a 25% chance of winning. You actually play the game and you only won 20% of the time.
Bruh.
There's something shady going on here. Can you sue McDonald's for this? Last time we talked about random variables, which were variables that countermeasure something about the outcome of a random process. An example I gave you was picking 5 random people. So in and of itself, picking 5 random people, you don't end up with a number. If you pick 5 random people, you just end up with 5 people, not a number. To force things to be numbers, we can countermeasure something about these 5 people. And the 2 examples I gave you was counting the number of people who play Wordle, and the other example was measuring people's heights and then finding the average height. So in both of those situations, you end up with a number at the end of the day. You end up with a random variable. Today we're going to talk about a very special type of random variable called a binomial random variable. And it's special in the sense that it's going to count something very specific. So binomial random variables are going to count the number of successes in a fixed number of trials. And the 2 important things here are, first, what it's counting. So counting the number of successes. And 2, a fixed number of trials. And what that means is whatever random process we're talking about, we're doing it a fixed number of times. All right, let me give you 2 examples of binomial random variables. The first example involves the random process of flipping coins. So say I flip 10 coins. Okay, flipping coins is my random process. I'm flipping 10 of them. Right? I'm doing it a fixed number of times, fixed number of trials. Now, what is it that I'm counting here? Say I'm counting the number of heads. So getting heads here is my quote-unquote success. Another example, so let's do an example where the random process is picking people. Say I pick 20 random people. So picking people is a random process. I'm doing it 20 times. I'm doing it a fixed number of times, fixed number of trials. Now, what is it that I'm counting here? Say I'm counting the number of people who play Wordle. So here, playing Wordle is what I consider to be a quote-unquote success. So success here just refers to either the special event that I'm counting or the special characteristic in people that I'm counting. Now I'm using the word success, but it doesn't have to be like a good thing. So I can also say pick 20 random students and count the number of students who drop my class. Dropping my class is the special characteristic that I'm counting. That's the quote-unquote success that I'm counting, even though students dropping my class is not really a good thing. So success just refers to the special characteristic that I'm counting. Now, there's 2 other requirements to being a binomial random variable. So let me write them here. The third requirement is that the trials need to be independent. And then the fourth requirement is that the probability of success needs to be the same for each trial. Now, I'm going to call these two requirements the fine print. Because for the situations that we're going to be dealing with in statistics, these two requirements are going to be met for free. So let me talk about these two requirements. For the coin example, okay, are the trials independent? Yes, they are. Okay, so independent refers to whether one trial affects what happens on the next trial. So for the coin example, when I flip my first coin, right, it's going to land on either heads or tails. Whether it lands on heads or tails is not going to affect what happens on the second coin. The second coin doesn't care what happens on the first coin. The second coin is not going to look at the first coin and say, oh, you landed on heads, I'm going to try to land on tails now. Right? That's not going to happen. So the trials are going to be independent for the coin example. The probability of success. Each coin has a 50-50 chance of landing on heads. So for each coin, there's a 50% chance of landing on heads. The probability of landing on heads is the same for each coin. So probability of success is the same for each trial. So the flipping coin example is a binomial random variable that satisfies all four requirements. Now, the picking people example doesn't quite satisfy requirement 3 and 4. And why is that? So let me go back to when we talked about the probability of picking like two people. So here we were finding the probability of picking two people who said plane was their favorite mode of transportation. And when we did those examples, I said for the second fraction, we have to take into account that we already picked one person for the first slot. So we have one less person to choose from total, which is why we had to reduce the denominator by 1. And because the first person was already a plane person, for the second plane person, we had to reduce the total by 1 because we have one less plane person to choose from. So in other words, what happens on the first slot, the first trial, did affect what happened on the second trial. In other words, the trials are not independent. And also, if I look at the probabilities, 44 out of 85, 43 out of 84, they're not the same. Right? So probability of success is not the same for each trial. So in the picking people situation, requirement 3 and requirement 4 are technically not met. But why is this kind of okay? So let's take a look at these two probabilities and let's actually find them. The first one, 44 over 85. So 44 divided by 85. 0.518. The second probability, 43 divided by 84. 0.512. Now, they're different, but they're pretty close. The first one, 0.518, 0.512. So 51.8% versus 51.2%. Pretty close. And that's with a total of 85 people. So if your population is large, so for our situations that we'll be dealing with in statistics, most of the time there are, because we'll be talking about things like people in Sacramento, right? That's millions of people. Students at CRC, that's tens of thousands of people. So if your population is large, the probabilities will be even closer. So if we're dealing with large populations, the probability of success will be about the same for each trial. And if we're dealing with large populations, the trials are going to be almost independent. So in the situations that we'll be dealing with in statistics, where we're dealing with large populations, requirement 3 and requirement 4 will be almost true. All right, we have 4 situations here. Some of these are binomial random variables and some of these are not. So what we want to do is we want to check these two main requirements. So first, are the number of trials fixed? Which means whatever random process we're talking about, are we doing it a fixed number of times? And then secondly, are we counting the number of successes? Which just means, are we counting the number of times that a special event is happening, like heads? Or in the case of people, are we counting the number of people to have a certain characteristic? Part A, a pair of dice is, that should say a pair of dice is rolled 10 times. So the random process we're talking about here is rolling dice. Are we doing it a fixed number of times? Yes, we're doing it 10 times, okay? So the fixed number of trials is good. Are we counting the number of successes? So in other words, are we counting the number of times that a special event is happening? So X is counting the number of times that a sum of 7 is obtained. So yes, we are counting the number of times that a special event is happening. And that special event is the sum being 7. So sum being 7 is our quote-unquote success. We have a fixed number of trials. We are counting the number of successes. So A here is a binomial random variable. Part B, a coin is tossed until a head appears. Is the number of trials fixed? There's nothing here that specifies how many times we're flipping the coin. We're flipping this coin until a head appears, which could mean we get a head on the first try. It could mean the second try. It may take us 10 tries before we get a heads. So here, the number of trials is not fixed. We're not doing this experiment a fixed number of times. So already, this is not binomial because the number of trials is not fixed. So number of trials not fixed. So C and D all involved picking random people. Part C, a random sample of 15 college students is obtained. Already number of trials fixed. Okay, so the random process here is picking random people. The question is, are we picking a fixed number of people? Yes, we're picking 15 people. So number of trials is good. Are we counting, so this we're talking about people, are we counting the number of people that have a certain characteristic? X here is the average number of units students are taking. So no, we're not counting the number of students that have a certain characteristic. We're counting here, well, we're finding the average number of units. So this would not be binomial because the X here is not counting the number of successes. So one way we can turn this into a binomial random variable is to say, let X be the number of students that are taking more than 12 units. So more than 12 units would be our characteristic that we're counting. So more than 12 units would be our success. So now that would be a binomial random variable. Part D, a random sample of 250 voters is obtained. Is the number of people fixed? Yes, it's 250, right? So the number of trials is fixed. Are we counting the number of people that have a certain characteristic? So X here is the number of people who support building a Costco in a neighborhood. So yes, we are counting the number of people that have a certain characteristic. And that characteristic is supporting building a Costco. So supporting building a Costco is the success that we're counting. Number of trials are fixed, 250. We are counting the number of successes. Success here meaning that they support building a Costco. This would be a binomial random variable. There's a nice formula for finding binomial probabilities. This is the formula, so let me tell you what some of these letters mean. The N stands for number of trials. The K stands for the number of successes. The P stands for the probability of success. And what are we trying to compute with this formula? We're talking about binomial random variables. And remember, for binomial random variables, the X is counting the number of successes. So what we're finding here is the probability that the number of successes is exactly equal to K. In other words, we're finding the probability of getting exactly K successes. And on the right side, we have NCK. The way you read that is N choose K. And the way you compute N choose K is this formula, N factorial, K factorial, N minus K factorial. Yes, those are exclamation marks. They stand for the word factorial. So we'll talk about that more when we actually do an example. And here's the example. Steph Curry is a 44% three-point shooter. In a game, he attempts 10 three-pointers, and the question is, find the probability that he makes exactly 7 three-pointers. So I see three numbers here. So what do these numbers mean? I see a 10, a 7, and this 44%. So he's shooting three-pointers, right? He's trying it 10 times. So the 10 here is the number of trials, which is N. We're finding the probability that he makes exactly 7 three-pointers. So making the three-pointer is the success, and we want him to make it 7 times. So 7 is the number of successes that we're looking for. That's our K. 44% is the probability that he makes it. So 44% is the probability of success. And anytime we're doing calculations involving percents, we should convert them to decimals first before we plug them into formulas. So 44% as a decimal, so the way you convert is move the decimal point 2 to the left. That would be 0.44, so 0.44. We're looking for, find a probability that he makes exactly 7 three-pointers. So we're looking for the probability of exactly 7 successes. So in symbols, we're looking for probability that the number of successes is exactly equal to K here is 7. On the right side, N choose K for us is going to be 10 choose 7. P to the power of K, P is 0.44. To the power of K, K is 7. 1 minus P, that's going to be 1 minus 0.44. To the power of N minus K. For us, it's going to be 10 minus 7. Now, let me simplify this 1 minus 0.44 and this 10 minus 7 because those are pretty easy to do right now. So what we have so far is 10 choose 7, 0.44 to the 7, 1 minus 0.44, what is that? 0.56 to the 10 minus 7, that's 3. And let me pause here and talk about what we have so far. So 0.44 is the probability that he makes it, and we want him to make it 7 times. What's this 0.56? 0.56 we got by doing 1 minus 0.44. And remember, anytime you do 1 minus, that gets you the probability of the complement. So 0.56 is the probability of the complement. The complement of making it. So what's the complement of making it? The complement of making it is missing, right? So 0.56 is the probability that he misses, and we want him to miss 3 times, right? That's what it means for him to make exactly 7 three-pointers out of 10. So we want him to make it 7 times, and we want him to miss 3 times. Now, what is this 10 choose 7 part here? Well, Making 7 out of 10, there's many ways that he can do it, right? He can make the first 7, miss the last 3. He can miss the first 3, make the last 7. He can miss the first 2, make the next 7, and then miss the last one. And many other ways that he can make 7 out of those 10. This 10 choose 7 is counting all the different ways that we can choose those 7 places that he makes the 3-pointer. Okay, so let's calculate this 10 choose 7. Now do that over here. So 10 choose 7. And like I said, the exclamation mark stands for the word factorial. So the formula says n choose, or n factorial. That's going to be 10 factorial on top. On the bottom, k factorial. That will be 7 factorial. And in parentheses, 10 minus 7 factorial. Let me simplify the 10 minus 7 because that's pretty easy to do right now. So we have 10 factorial on top, 7 factorial, 10 minus 7 we know is 3 factorial. Now, what does this factorial mean? 10 factorial just means 10 times 9 times 8 times 7 all the way down to 1. 6 times 5 times 4 times 3 times 2 times 1. 7 factorial means 7 times 6 all the way down to 1. 5 times 4 times 3 times 2 times 1. 3 factorial means 3 times 2 times 1 all the way down to 1. Okay, so we have a whole bunch of numbers here. We have some of the same numbers on top and on bottom. So we can cancel these out. Notice that I have 7, 6, 5, 4, 3, 2, 1 on top, but I also have 7, 6, 5, 4, 3, 2, 1 on bottom. Those can be canceled out. So let's cancel those out. And what I have left is 10, 9, 8 on top, 3, 2, 1 on bottom. And these are multiplied. So 10 times 9 times 8 on top, on the bottom 3 times 2 times 1. Now what you could do here is simplify even further. So for example, the 8 and the 2 can cancel, leaving a 4. 9 and 3 can cancel, leaving the 3 on top. Or you can just enter it into a calculator just like this. So I'm just going to enter it into a calculator just like this. So on top, 10 times 9 times 8. On the bottom, 3 times 2 times 1. I get 120. Okay, so this 10 choose 7 is 120. So there's 120 different ways that we can choose the 7 places out of the 10 where he's making it. 0.44 to the 7 times 0.56 to the power of 3. So let me enter this into a calculator. 120 times 0.44 to the power of 7 times 0.56 to the power of 3. And I get 0.067. So if he takes 10 shots, the probability that he makes exactly 7 is 0.067, which as a percent would be 6.7%. Now, most of the time, we're not interested in the probability of getting exactly something, right? Most of the time, we're actually interested in things like part B. What's the probability that he makes at least 7 3-pointers? Because say if he makes 7 3-pointers, the Warriors win. If he makes more than 7, the Warriors also win. So if all you care about is the probability of the Warriors winning, then you care about things like this. What's the probability that he makes at least 7 3-pointers? So in symbols, what are we looking for here? In symbols, we're looking for a probability that the number of successes is 7 or more, right? 7 or more would be greater than or equal to 7. How would we compute this? If he takes 10 shots, making 7 or more could mean making 7. It can also mean making 8. It can also mean making 9. It can also mean making all 10. Okay? So to find x greater than equal, probability of x greater than equals 7, we actually have to take into account all of those things. So the probability of x greater than equals 7 would mean we have to compute the probability of getting exactly 7 plus the probability of getting 8 plus the probability of getting exactly 9 plus the probability of getting exactly 10 successes. So we already found probability of getting exactly 7 successes, and that was 0.067. Now we have to do it again with an 8 there. Then we got to do it again with a 9 there. Then we got to do it again with a 10 there, and then add it up. It's kind of a pain. The good news is at the end of the lecture, I'm going to show you how to find this on a calculator with R. In the last lecture, we talked about mean and standard deviation for regular random variables. And the way to find it is we started with the probability distribution, which was a list of all the possible values of x along with their probabilities. And I'm going to make up some numbers here, like 2, 4, 6. And then we had some probabilities. To find the mean, we had to add on another column, x times p of x. And then to find a standard deviation, we had to add on another column, which was x minus the mean squared times p of x. And that was kind of a pain, right? So the good news is for binomial random variables, there are really nice formulas for the mean and standard deviation, where you don't have to make this table. So for binomial random variables, to find the mean, it's just going to be n times p. Okay, n, number of trials, p, probability of success. You don't have to do a table to find it. To find the standard deviation, you also don't need a table. The formula for finding a standard deviation is big square root n times p times 1 minus p. So that's why binomial random variables are so nice. All right, so I have everything I need now to talk about McDonald's. McDonald's has this Monopoly game where they claim that 1 in 4 wins. So 1 in 4 is equivalent to 25%. So they're claiming that you have a 25% chance of winning. Now say you and your friends actually play the game 530 times. How many times would you expect to win? Keyword here is the word expect. So anytime you see the word expect, I'm asking about the expected value. And expected value, another word for expected value is the mean. So I'm asking about the mean here. What is the mean? So this is a binomial situation, right? We're playing this game 530 times. That's the number of trials. We are interested in the number of times that we win. So we are interested in the number of successes. This is a binomial situation. So finding the mean for a binomial situation is pretty easy. N times P. Right, the formula is N times P. N, number of trials. How many times did we play this game? 530 times. P is the probability of success. What's the probability of winning? 25%. As a decimal, 25%, move decimal 2 to the left. That will be 0.25. Okay, so on a calculator, 530 times 0.25. 132.5. So if you play this game 530 times, you would expect to win around 132.5 times. Now say you guys actually played the game and you only won 108 times. Is that too low? Is that too low that you would say something shady is going on? Could you sue McDonald's for winning only 108 times? Say you do sue McDonald's. What is McDonald's going to say? I'll tell you exactly what McDonald's is going to say. McDonald's is going to say this. Look, 132.5 is a theoretical number. So just like when you flip 10 coins or flip a coin 10 times, in theory, you should get half heads, half tails, right? In theory, you should get 5 heads, 5 tails. Now, if you, in reality, flip a coin 10 times, are you always going to get 5 heads, 5 tails? No, right? If you flip a coin 10 times, sometimes you get more than 5, sometimes you get less than 5. Same thing here. 132.5 is the theoretical expected value. If you actually play the game 530 times, some people will get more than 132.5, some people will get less. You guys were just unlucky and got less. This is perfectly normal. That's what McDonald's is going to say. Is it really? Is it really normal? Or is winning only 108 times unusual? So we know how to determine whether something is unusual or not unusual. And that involves finding the mean and the standard deviation and then making the empirical rule picture. So let's do that in this situation. We have the mean already. We'll need the standard deviation. The formula for standard deviation is big square root n times p times 1 minus p. So big square root n times p times 1 minus p. In our situation here, n, number of trials, number of times you played the game, 530. P, probability of success, it's 25%, but we need to convert that to a decimal, so that's going to be 0.25. And then 1 minus p, so 1 minus 0.25. And let me enter all of that into a calculator. So square root, inside the square root, 530 times 0.25, parentheses, 1 minus 0.25. 9.969. Okay, that's the standard deviation. So to decide whether something is unusual or not unusual, we're going to make the empirical rule picture. So put the mean in the middle, 132.5. And then I want to go up 2 times and down 2 times. So up 2 times and down 2. So to go up 2, we're going to start with the mean, so 132.5 plus 2 times the standard deviation. So plus 2 times 9.969. And then to go 2 down, we're going to do start with the mean, so 132.5 minus 2 times the standard deviation. All right, so let me find those two numbers. So for the lower number, 132.5 minus 2 times 9.969, 112.562. Okay, so that's one number I want. The upper number, 132.5 plus 2 times 9.969. And that is 152.438. Okay, so remember, these are going to be the boundaries, the lower and upper limit for what's considered unusual and not unusual. So if you're on the outside, right, that's considered unusual. If you're in between, that's considered not unusual. Or another word for not unusual, remember, is usual. So where is 108? Is 108 in the unusual zone, or is 108 in the not unusual zone? Where is 108? Here's 112. 108 would be to the left of that, which would put it in the unusual zone. So, no, McDonald's. Winning only 108 times is not normal. Winning 108 times is unusual. So something shady is going on here. So as I promised, we're going to use R to help us find binomial probabilities. And the two commands in R that we'll need are dbinom and pbinom. Dbinom is for a situation where we're looking for a probability of x exactly equal to something. So that's going to be the situation where we're looking for equals to something. Pbinom is for the situation where we're looking for a probability of x less than or equal to something. And those are the two situations that R is going to help you with directly. Now, there are other situations, such as greater than or equal to, less than. So those situations, we're going to have to do a little bit of adjustment in order to use R. So let me actually go through here and read what we're looking for. Part A, find a probability that exactly 16. Part B, find a probability that more than 17. Part C, find a probability that fewer than 20. So these are phrases that we encountered in the last lecture. And at the beginning of the last lecture, I talked about those common phrases. At least 21, more than 5, fewer than 15, no more than 2, exactly 11. And we talked about what that meant in math symbols. So if you need to, go back to that table. So here, exactly 16. That situation is exactly, that's an equals. So that's the equals situation. More than 17. More than, greater than. That's the greater than situation. Fewer than, less than. Okay, let me go to the next page and talk about those also. Do the same thing. Part D, what is the probability that no more than 46? No more than. What does that mean? No more than. No more than. Less than or equal. Part E, what's the probability that at least 15? At least 15? At least greater than or equal to. Part F, find a probability that at least 1. At least 1, kind of same thing here. At least is going to be a greater than or equal to. All right, so now let's go back and actually talk about how we actually compute this stuff. Part A, a survey sponsored by the Vision Council showed that 79% of adults need correction for their eyesight. If 20 adults are randomly selected, find a probability that exactly 16 of them need correction for their eyesight. So in symbols, what I'm looking for here is probability that x is exactly 16. And exactly 16 we said translated to equals 16. Now, if you're in a situation of either equals or less than or equal, then we can use directly one of these commands. We're talking about equals, which is the first situation. The command we're going to be using is dbinom. So dbinom, parentheses, number of successes. Number of successes is the k, which in our case will be 16, comma, number of trials. Number of trials, when we talk about picking people, is going to be the total number of people that we're picking. So we're picking a total of 20 adults. Comma, probability of success. Probability of success is going to be the percent. Anytime we're doing calculations with percents, we want to convert it to a decimal first before we plug it in. So 79% as a decimal. So move the decimal point 2 to the left, 0.79 or 0.79. And then we'll just type that into R. So in R, dbinom, parentheses, 16, 20, 0.79. And then we'll round to 3 decimal places. This is 0.217. So if you're in the equal situation or the less than or equal situation, then you'll just use either dbinom or pbinom directly, and you're done. Part B. The National Coffee Association reported that 63% of U.S. adults drink coffee daily. A random sample of 25 U.S. adults is selected. Find a probability that more than 17 of the sample adults drink coffee daily. Okay, in symbols, what we're looking for here is probability that x is more than 17. We said translated to a greater than 17. Now, notice that greater than is not one of the ones that R does directly. R only does equals and less than or equal. So anytime you are doing something that's not one of these, we have to think a little bit. We have to make an adjustment. And the idea is to rewrite greater than 17 so that it has a less than or equal, so that we can use pbinom. And to help me, I'm going to make a number line. And on this number line, I'm going to put 17. And also the numbers around 17. And really, I only need the number that is above 17, 1 above 17, and a number 1 below 17. So 1 above 17 will be 18, 1 below 17, 16. And now the question I'm going to ask myself is, what numbers are greater than 17? What numbers am I talking about? Greater than 17, right? It doesn't include the line, so it's not greater than equal. It's strictly greater than 17. Greater than 17 would mean 18 and to the right. Right? Greater than 17 are the numbers that are 18 and to the right. That's what I'm looking for. That's what I want. $18 to the right. Notice that R only does less than or equal, which is to the left. So the idea here, anytime you're looking for anything that is to the right, the idea is to first look at the left part. The left part would be 17 and to the left. And the idea is rewrite that left part using a less than or equal. And then to get the right part, which is the complement, you just have to do 1 minus that. Okay? Left part, 17 and to the left, would be written as less than or equal 17. Okay? Notice that now I've introduced the less than or equal like I wanted. That's the left part. Because I want the right part, which is the complement, we just have to do 1 minus. Okay, we're going to do 1 minus the left part, which is less than or equal 17. And that tells me what I need to type into R. So what I'm going to type into R is 1 minus less than or equal 17 is now going to be a pbinom. So we're going to do pbinom. Number of successes, that's our K, which is the 17. Comma, number of trials. When we're picking people, that's the total number of people we're picking, 25. And then comma, probability of success, that's the percent, but remember to convert it to a decimal. 63% as a decimal, move the decimal 2 to the left, 0.63. Okay, and that's what you're going to type into R, including that 1 minus. So we're going to type into R 1 minus. Be careful that this is a pbinom now. Parentheses, 17, comma, 25, comma, 0.63. Rounded to 3 decimal places, this is 0.237. So once again, anytime you are looking for something that's to the right, idea is look at the left part, rewrite it with a less than or equal, and then do a 1 minus. And that will get you the right part. Part C. A new medical procedure produces side effects in 25% of patients who receive it. In a clinical trial, 60 people undergo the procedure. What is the probability that fewer than 20 have side effects? In symbols, what I'm looking for here is probability, x. Fewer than 20, we said translate it to a less than 20. Less than is not one of the two that R does directly, right? R does less than or equal. Here, I want a less than. So I do have to make an adjustment. And to make an adjustment, I'm going to make my number line. I'm going to put the 20 on the number line, and then the numbers around 20. And really, I only need the number that's one above, which is 21, and one below, which is 19. And now I'm going to ask myself, what numbers do I want? Less than 20. What numbers are less than 20? So that's strictly less than, so that means 19 and to the left. Right, that's what I want. Okay. Anytime you're looking for something that's to the left, all you need to do is rewrite it using a less than or equal. Okay. 19 to the left is the same thing as saying less than or equal to 19. Okay. That's 19 or less. 19 to the left. So we rewritten a less than so that it has a less than or equal. Because it has a less than or equal, now I can just use p binom. So this is telling me that what I'm going to type into R is going to be p binom number of successes, that's going to be the 19, comma, number of trials, that's how many people are we picking total here, 60, comma, probability of success, that's the percent, but remember, convert that to a percent or to a decimal, 0.25. Okay, that's a command I'm going to type in. And my answer, p binom, parentheses, 19, 60, 0.25. Rounded to 3 decimal places, this is 0.908. Okay, notice that in part B, because I was looking for something to the right, that was what I wanted, something to the right, my final answer had a 1 minus. In part C, I'm looking for something to the left. My answer did not have a 1 minus. Part D. Airlines often sell more tickets for a flight than there are seats because some ticket holders don't show up for a flight. An airline estimates that 90% of ticket holders actually show up for the flight. If the airline sells 50 tickets, what is the probability that no more than 46 of the ticket holders will show up for the flight? In symbols, what we're looking for here is probability of x, no more than, we said translate it to a less than or equal, 46. Okay, notice that we're looking for a less than or equal, which is exactly one of the ones that R does directly, so we don't have to do any adjustments. Less than or equal, p binom, and then the 3 numbers. So for this one, because it's less than or equal, it's one of the ones that R does directly. We just have to do p binom. Number of successes, that's the 46. Comma, number of trials. As a hint, that's always going to be the bigger number. That's 50. Comma, probability of success, that's the percent. 90% as a decimal, so move the decimal 0.2 to the left, that's 0.90. And then we'll just type that in. P binom. Parentheses, 46, 50, 0.90. Rounded to 3 decimal places, this will be 0.7. This is going to round to 750. Part C. Suppose that 63% of people are right-handed. If 30 people are randomly selected, what's the probability that at least 15 of them are right-handed? In symbols, what I'm looking for here is at least, we said was a greater than or equal to 15. Now, greater than or equal to is not one of the ones that R does directly. R only does equals and less than or equal. So that means that we have to make an adjustment here. So I'm going to draw my number line. I'm going to put 15 on there. And then the numbers around 15. So the numbers that are one above and one below. So one above 15 will be 16. One below will be 14. And now I'm going to ask myself, what numbers are greater than or equal to 15? What numbers am I talking about? Greater than or equal to 15 means 15 and to the right, right? I also want to include 15. That's what the line below means. Greater than or equal to 15 means include 15. So I'm talking about 15 and to the right. Okay, that's what I want. And just like on the previous page, part B, anytime I'm looking for something to the right, the idea is look at the left, rewrite it with a less than or equal, and then do a 1 minus. Okay, look at the left. The left is this 14 and to the left. Okay, 14 to the left is rewritten as less than or equal to 14, right? Less than or equal to 14, 14 or less, 14 to the left. To find the right side, that's the complement. All we do is do 1 minus that. So 1 minus less than or equal to 14. That tells me what I need to type into R. So I'm going to type in 1 minus less than or equal was P binomial. Number of successes, that's the 14. Number of trials, that's going to be the bigger number, which is 30. Or in the case of people, it's the number of people that we're picking. Probability of success, that's the percent, but convert it to a decimal. So 63% as a decimal, 0.63. That's what I'm going to type into R. So 1 minus P binomial, parentheses, 14, 30, 0.63. Rounded to 3 decimal places, this is 0.4 or 0.950. Part F. Of all the registered automobiles in California, 8% failed the state emissions test. 12 automobiles are selected at random to undergo an emissions test. Find a probability that at least one of them failed the test. In symbols, what I'm looking for here is at least 1, which in symbols we said was greater than or equal to 1. Greater than or equal is not one of the ones that R does directly. R only does the equals and a less than or equal. So the idea here is that I do need to make an adjustment. And to help me, I'm going to make a number line. I'm going to put the 1 on a number line. And I'm also going to put the number that is 1 above and 1 below. So 1 above will be 2, 1 below, 0. And now I'm going to ask myself what numbers are greater than or equal to 1. So greater than or equal to 1 refers to what numbers? Greater than or equal, so that means 1 and to the right. So 1 and to the right is what I want. Okay, anytime I'm looking for anything to the right, the idea is find the left part, rewrite it with a less than or equal, and then do 1 minus. So the left part is 0 and to the left. Okay, 0 and to the left is rewritten as less than or equal to 0. Okay, less than or equal to 0 is 0 or less, 0 or less, 0 to left. Because I want the right part, which is the complement, do 1 minus. So 1 minus x less than or equal to 0. So that's going to help me tell me what I need to type into R. So 1 minus less than or equal is a P binomial. Number of successes, that's the 0, comma, Number of trials. Number of trials is the bigger number, 12. Probability of success, that's the 8%, but convert it to a decimal. So be careful here. 8% as a decimal is not 0.8, right? If I move the decimal point 2 to the left, it's actually 0.08. So type this into R. 1 minus p binom 0, 12, 0.08. 0.632. Okay, that's the final answer. And the answer, or the command I typed into R, was this part. All right, I'm not done with McDonald's yet. So earlier, we said that if we play this Monopoly game 530 times, it would be unusual to win only 108 times. So now we're in position to say how unusual is that, right? How unusual is it to get that low of a win number, 108 times? So what is the probability of winning 108 times or less? In symbols, what we're looking for here is probability that x is 108 or less would translate to a less than or equal 108. Less than or equal is one of the ones that R does directly. So this is going to be just a p binomial. Number of successes, that's the 108. Comma, number of trials, how many times did we play this game? We played this game 530 times. Probability of success. McDonald's is saying that the probability of success is 25%, which as a decimal would be 0.25. Right, so in R, p binom, (108, 530, 0.25. Rounded to 3 decimal places, this is 0.007. So if we play the Monopoly game 530 times, there is a 0.007 probability, which as a percent would be 0.7%, less than 1% chance that you will win that low, 108 or less. That's a little shady. That's saying that winning only 108 is extremely rare, less than 1%. So this is like saying, if you flipped a coin 10 times and you got all heads, right? Heads, 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 all 10 heads. That's something extremely rare. And there's 2 possible explanations for this. Either you are just extremely lucky to get all 10 heads, or something's wrong with the coin. The coin is not a fair coin. Here, right, because this probability is so low, what this is saying is that either we are just super unlucky to win only 108 times, or McDonald's is doing something shady. Which one is it? All right, have a great day. See you in the next video.